Okay. Been doing any cool things with machine learning? No. Those are really. Oh yeah, I know.
You get what you said?
Oh.
No, I don't know. What is the accelerator? What's the difference?
So we're just an accelerator and an incubator. An incubator is like ACDC, takes apart classes, you know, financial modeling. An accelerator will take you through, let's say, 3 to 4 month program. They'll give you like maybe $120,000. The value is not million, and then they introduce you to almost a venture capitalist, portfolio company, and you can use other people in the network. And people in the network are drop off based on the boundaries of all these people. And you can really have access to all these, directly to all these companies. You can get literally within some companies.
Okay, I see. So you are under evaluation. Did it work with this project? You told me once. We never talked about that. These guys that they were going to pay $5,000.
I decided not to move forward with that because they were asking. First of all, they were told me only 50 megabyte, data file. Not too hard to do. But once I found out that it was 50 gigs, I realized that we were finding more development that I had going on in that point. And the question is, if you go down in that direction, is that pretty much correct?
You still have the contact? You can do something here. Yeah, hello. The library, maybe Logic Blocks can do, we'll see. Yeah, if you still have the contact, I thought it was, it would be nice to, when you come with 50 gigabytes of data, then they have to say something for a pilot. So I figured out why last time it wasn't really writing smoothly. It was because I needed to clean it. So, Angelo, how's your spare time?
So today,
or in general, your time outside of Kampala?
all of my
No, straight up all the time.
So there's some work we can, if you have time. Are we being recorded now? Recording. Okay. Yeah, we can talk about that. You want to help in some project. Machine learning.
It's pretty easy, except unless you get into really crazy stuff and start breaking things. That's a little more theory. You need the theory.
Okay.
I would say.
So, Lynn, I heard you have some problems with the audio. How is audio right now? Is it too bad to Google? Can you hear it?
Hello?
Hello? It's still a little bit fuzzy. So can people respond? How's the audio right now? Lynn says it's fuzzy. Are you using your you just saw your husband? I can hear you fine, but again,
You have to go through.
there's background sound because people are talking. So Renel, have you attended before, Renel? I'm pretty bad with. Okay. Have you come here on site? Were you on site last time? I think you were on site. Yeah, I think I remember you now.
Yeah. But doing like a speed processing and simple selection.
Aha.
And really turning it down to core essentials. The speed algorithm is what is pattern and requiring different steps of variables. And some algorithms have speed selection built in, and some don't whatsoever. So it's like doing the speed processing faster the entire time of that. So for me,
Yes. So that's what I'm working on right now to program people.
How much time does that take? Doing machine learning doesn't just have time if you have the right.
Well, you can use the machine learning to do the pre-processing. That's kind of like that's what Trifactor is trying to do to prepare the data. So 12:03. Let's wait 5 more minutes. Yeah, unfortunately, a lot of people sign in, but then they don't show up. So
Not me, I just say that.
yeah, you are except
So is there an easy way to do that? I was thinking that, and I imagine because each algorithm may, let's say we're doing regression. There's so many different regression algorithms. This is like 50 popular regression algorithms that really exist, and they're all doing regression in slightly different ways, or at least dividing their output and doing the prediction, let's just say hypothetically, in slightly different ways. But I believe because they go about mathematically deriving what the answer is in slightly different ways, they'll all have a slightly different
assumption.
Well, yes, of course, they all have slightly different assumptions, but I wonder if that's going to change what kind of pre-processing we have to do.
By the way, talking about that, there's a very interesting course going on at NYU, and they have all the material online. NYU.
Is it Coursera or something?
No. And then it's last. Okay. You know, the class is taught by some very, very great people, like John Langford and Jan LeCun. So.
I'm taking a lifetime out in order.
No, you're taking Coursera with the different intelligence.
Including one programming style.
Programming style?
Yeah, that's interesting. How do you program?
Okay, so you got the link that I just sent on. It's on the chat.
And maybe if you post it to the meetup in general,
you know, I figured out if you could, I'm going to give access to people posting things. Actually, you can post it now. You can post it on the meetup. Because it turns out that this meetup is, so we're about to start then. It's pretty unique because, if you see the other meetups, there's usually a different presenter every time. So I do the presentation every time. And preparing the class, preparing the classroom, adding the notes takes time. And I'm kind of like reached my limit, so I'm going to open it to people to contribute more if they want. So, yeah, if any of you want to take it and post it on the... It's a great course. A little bit advanced, but they explain it very well if you want to. I think it's better than the Coursera one, from what I've seen.
That's more of an overview.
Yes, that's like more practical.
Yeah, I'm gonna sign up for that.
No, the Coursera is good too. I mean, it's more introductory. But this one also is more like that. Understand it online and else. Many people.
So what do you think? Pre-process, could one do pre-processing each algorithm, or pre-process the features on time, whatever?
Usually there's a standard way, one time. So did any of you have the chance to read the paper?
One row, and I will do
Okay, so...
May I see the paper?
Yes, I have extra copies. Okay, so it's actually the first paper, and I've printed 2 extra ones. So today, as I announced, we're going to work on something that people have expressed deep interest, which is finding communities in graphs. And I've chosen the easiest, probably. Is that the new one? The easiest, probably, algorithm class of doing that, and the ones that scale. So this paper that you can, first of all, let me make this announcement. All the material, whatever we're using, is posted on the class notes. So we are working on the paper called, Defining Network Communities Based on Ground Truth by Yuri Leskovich. So Yuri Leskovich is a professor to follow. He's one of the gurus on graphs. He's a student of Palutzos from Mellon University. Who is kind of like the god of graph mining. He has about 20 best paper awards. He's a really nice guy. I think at some point Georgia Tech tried to recruit him, but eventually he stayed at CMU. So Yuri is probably one of his best students. He was also recruited by Georgia Tech, but he preferred to go to Stanford. I think Yuri is more geared around the social networks. Palutzos is more general. So he's Slovenian. So yeah, find his website, Google him, and follow his. He has several talks over there. Now, there's a very nice book as a reference book which I have presented before. It's called Network by M.E.J. Newman. Newman is actually a physicist, but he has done great work on networks, and he's the one who discovered the modularity clustering on graphs. It's an objective function on graph, and you might have seen it on the.
When you say modularity, is that basically saying that there's multi-dimensions within modeling things?
So modularity is kind of like when you're trying to partition a graph, what are you trying to maximize? We're going to see in the paper today, you're trying to make sure that the links between your community are maximized, or the links between different communities are minimized. We have conductance. We're going to go through all this. So Yuri Leskovich, if you download the paper, it's like one of the co-authors. Mohsen is asking if I can spell again his name. Yuri Leskovich. It's the second author, the professor of the paper that we're reading today. Now, I was talking about Newman, the book, Networks. Okay, he is also as a reference in the paper, one of his papers. And then I have another book which I don't have it with me, but I have posted on the class notes. It's called Linear Algebra, the Language of Graphs, or Graphs, the Language of Linear Algebra, which is probably the best way to understand graphs. Many people have, actually very few people know about this book, but the people that have read it, they said, Nick, after I read this book, graphs look very easy to me right now. Now, I also want to point out two important references. So the whole paper is basically based on these two papers, which again, if you can't read it from here, you can see it in the class notes. The first one is called Local Graph Partitioning Using PageRank Vectors from Yahoo Research and Sunday. These are all papers like 2005, 2006. And the other one is called Communities from Seed Sets. So basically the paper that we're going to study today is kind of like a combination of these two. And of course, even more stuff than that. Are there any questions so far? Please feel free to interrupt for questions.
Can you repost it and the link in the
Yes. Okay. Yeah. So I talked about the NYU class on machine learning. Very, very interesting talk. If you want to go deeply in there, want to learn how Vocal Wabbit works, it's taught by these people over there. John Langford, Jan LeCun is one of the winners in the Netflix competition, and Langford these are legends in machine learning. So let's start with the paper. So the paper, what they do over here is they said, we're trying to find communities, and there are several algorithms for finding communities in a graph. So they start from a more kind of like review perspective, where they're saying that, okay, let's say that we have ground truth about communities, and there's about, I think they present 13 different metrics for defining a community. Let's see how they all behave. So if you go to page okay, page number 4. Okay, and they call. You can also see the paper online. If you go to the class notes, the paper is posted, okay? So, by the way, yes, so if you please go to have the paper handy so that I can refer with you in electronic format. So, it gives all the scoring functions. Let me, excuse me, do we have a question? No, I thought somebody was talking. Okay. So scoring function. So when we have a graph, you notice that today the images are smoother. It turns out that these boards, they need to be cleaned once in a while. And that's what I did. Rubber alcohol did the job. Rubbing off. No problem. So it says that for every community, so let's say we have a graph with really two communities. Okay. Now, here you have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 nodes. If we had a complete graph, how many edges is it possible to have? So if you have a graph with 8 nodes, can somebody give an answer?
What the nodes connected themselves?
How many edges? What is the maximum number of edges you can have on a? Yes, you are exactly right. So if you see the first score, so Angelo said it's 8 times 8 minus 1 over 2. This is very, very well known from Euclidean geometry. You might have done it as, inductive logic, how you prove that. It's like from high school, I don't know, university. We did it in high school. in Greece. But so if you have n points, how many lines you can go? I think that's that. So, in order to, if you have like good community and everybody's connected to everybody, we usually call that what? A clique. If everybody is connected to everybody, this is called a clique in graph theory. Then that's very good. So, in order to evaluate a community to see how good community is, you take the ratio, and that's like the internal density, which is the number of edges you have here. We have 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10, and this would be, 4 times, this is, so 10 over 28. So this is approximately, let's say, 0.3, whatever. It's something less than 0.3, something more than 0.38. Okay. So Angelo is really a human computer, which is pretty good, Typically, if you think when we go to, to millions of nodes, typically, a graph, just to give you an idea, the graphs have to be sparse. If they are dense, there are many reasons why a graph cannot be dense. First of all, if it's dense, it's explosive, it's impossible to process it. So, for example, if we had 1 million nodes, that would be 10 to the 6 times 10 to the 6 over 2, so approximately would be 10 to the 12. Typically, in our graph, the number of edges is k times the number of nodes. So on 1 million graph, you will have something like 10 to the 6 times k, and k could be like the average degree would be 20. So this density, whatever, it would be something very small, would be 20 to the minus 6. That order, 10 to the minus 5. So very, very small. Okay, so this is one measure. And there's another reason why a graph has to be sparse, which has to do with nature, why nature produces sparse graphs, because dense graphs are actually very unstable. They're very unstable because if there is a failure or an infection somewhere, a bad malicious behavior, on a sparse graph, it takes time, it takes logarithmic time to expand everywhere. But in a dense graph, it can propagate everywhere in just one step. Because every node is connected with everybody else. Like a scissor in your brain could burn your brain immediately. Your brain is a sparse graph. An infection on a computer that is connected to everything else, since, Angela, you're from Dambala, it will infect everything at once. So there's a good reason for having a sparse graph. So the second measure is called edges inside. It's very simple. It's just the number of edges. So the first one is kind of like normalized. The second one is kind of like more absolute. Now, the average degree, we know what the degree of a node, you know what it is. It's the number of edges that live or end on the node. So, for example, here, we have 8 nodes here, and here we have 1, 2, 3, 4, 5. So in total we have 13 nodes, and I think we have 18 nodes, 18 edges. So the average degree will be 18 over 2 over 13. Did I measure everything correctly? 13 nodes. So it's something over here. Yeah, I think I'm right. So it's let's say around 2. On the average, like 2. I must have done something wrong. It doesn't make sense. Actually, it's 2 times that. Because the edges, this is an undirected graph, so the edges can be incoming around. So this is around what, 3.5. Yeah, which makes sense. Like if you take a random, node and you count the average edges with 2 to 4 to 5. Okay, inside the communities, of course, we see that this is a little bit higher. So the next one is fraction over median degree. So basically, you know what the median is. So you find the average degree, you find the degrees of every. Does everybody knows how to compute the median? So you take all the nodes with their degrees and you sort them from high to low. It doesn't matter, and you find the one in the middle. So the one kind of like counts of how many nodes. Like when you're working with medians are more robust. I mean, you know what the problem is, that sometimes the average can be skewed in the sense that, what if you had a node, if this node had 1 million, if this node over here had 1 million degrees and the rest had 3, the average would be around, let's say, 100 million. But then 99% of the nodes will be less than the average and 1 will be above the average, okay? Now, the median is more robust because what it does is that, it will take all the nodes, sort them according to their degree, and pick the node that divides the things, divides the set equally, okay? That's kind of like, if you're in a company and the CEO gets 1 million and the rest are getting like 10,000, the average salary can be 100,000. But the median salary would be around 10,000 because it's shorter. So that's another degree. So that's like a more stable, more robust one in case you have outliers. Now, the most important one, from my opinion, is the triangle participation. I mentioned that last time we were talking about GraphLab, and I will keep mentioning that. Triangles are very, very important for a community because they are, so first of all, triangles are clicks of order 3. Is anybody coming in? No. Doors open. So triangles are very, very important. I mean, you will notice that, within this community, like inside the communities, the number of triangles, if you see every point almost participates in at least one triangle. And just, you open the door. Did anybody close it? I think it's open. Okay. That's great. Hi. Do we need an extra router? There's an extra router over here, or we need yes. Okay, so the triangles, the number of triangles is very, very important. Now, these are all, scoring functions within. What do we need? We need what? Okay.
You can take wireless and like that.
But wireless doesn't work. Okay. You don't have to eat all your bandwidth. So anyway, so these score the communities inside. So when you're doing community detection, you are saying, so somebody, for example, there's something problematic with that. And problematic is that if somebody was taking, this as a community, yes, this is a community because it has too many triangles, the density is very high, but there's a lot of edges going out, to other nodes. So it might be a case where you have a community nested in a bigger community, so, I mean, it's obvious from this that you're having a bigger one. So, I mean, if somebody gives you a set of nodes and asks, is it a good community, you can take all these internal scores and say, oh yes, these people form a community, but I'm not sure, on a global scale that they are an isolated community. So that's why we need to keep in mind scoring functions that they take into account things with the outside world. So, for example, there's something called the expansion. So for this particular, community over here, there is a big expansion because there's a number, like the number of outgoing edges is significantly high compared to the number of the internal, edges. Compared to the number of nodes, I think it is. Yes. And by the way, there's a term called expander graph. If you read the seminal paper about the Google PageRank, they say that the web is an expander graph, which means that if you take any subgraph you're taking, the number of outgoing edges are always higher than the number of internal edges. So obviously, when you want to detect communities, so when you're doing what we call in machine learning discriminative analysis, okay, so the first one was like more generative analysis. Whatever I'm given, does this form a cluster? Is this like a community? I see you are rolling your eyes. You get the analogy? It's a generative because, we're looking only the data at once. We're not looking at the outside world. When you're looking at the expander, the external measures, it's like a discriminative analysis, like how, class one is, or cluster one or community one is compared to another community. There is a lot of disconnection between them. The other one is the cut ratio, where basically is kind of like a normalized, expander. Basically, it measures the outgoing edges versus the possible edges that you can have between these nodes. What you see over there as n times n minus s is it measures. Sorry, let me rephrase that. It measures, like, for this number of nodes, what are the possible outgoing edges. So, for example, in this subgraph over here, that I have n nodes, and then I have 1, 2, 3, 4, 5, whatever m nodes outside of this subgraph, there are n times n minus s possible edges going out. So there's a lot of it, like there could be an edge from here to this node. It doesn't exist. So it's a normalized method. Do we have a question? Does anybody want, anytime you want, you can interrupt and ask questions. I don't want to make this as a monologue. So, are you set up? Did you connect to the internet with?
Yeah, it's not working, but I can make it.
You can share screen with. So I wonder why it's not working.
So are there dates? These are metrics?
These are all metrics, and there are some ones that, and then you have the number, the next class, which is.
What do we measure these metrics against?
So you want to either minimize or maximize. Okay. So for example, the internal measures you want to maximize. For perfect community, you want to maximize the number of internal densities. Yeah. So the external, you want to minimize the expansion. Okay. And
we want to minimize external, maximize internal.
And the number C, which is scoring functions that combine internal and external, you still want to minimize. Okay. Because the ones that combine both, you could maximize if you take the inverse of that. So the conductance, has to do with physics. If this was a flow network, like flowing heat or flowing electricity, you want to make sure that the flow is minimized. And maybe it doesn't make sense to get into all these details. So the normalized cut is probably the most popular. Now, I'll go forward to, frankly, you're all professionals, and if your boss tomorrow asks you to do a community detection for a project that you have on a graph, you don't have to try everything. Even, the truth is that any measure you will take, it's going to work. Now, the modularity is probably the most interesting one because it doesn't really fall into any category from the previous one. Because if you see the objective function, the objective function is whatever we call modularity. Sorry. somebody needs to mute. So I call it F of S. S is the community. Again, for those of you who just joined, we are on the page number 1, 2, 3, 4. Okay, on the left column. So it does something very, that's like a very nice trick that I'll mention the analogy to K-means. So sometimes in machine learning, if we're trying to find out if there is structure, we always compare to the random case. Okay? So this thing says that, you have this graph like this one before. Now, if I start randomly, so every graph right here has a certain degree. Like, for example, this one has degree 3. Okay, this one that I'm pointing. Now, what I'm doing is that I'm taking this every node and I'm splitting it, every edge. Right. So I split the node, the edge, and I randomly rewire it to a different, a different node. So basically, it says the following. You're taking the network, you're taking the community. Okay, let's say you're taking this community over here, and you count the number of edges that there are, between these nodes. Then you are taking every edge, you split it in two, and you rewire it to any node inside, outside, wherever, in the graph. So it's like this is the random graph model. There's a whole class of algorithms about, and Yuri has also done a lot of work, like graph formation. How do we form a graph? How is the graph formed? And the random graph means you have an edge, and the edges, you have a node, and the node randomly, connects to another node. And this is how you put the edges. There are, for example, other graph formation algorithms that they say that the node always connects to the node with the second highest degree. So you have a network, and I come in, so it is a friendship network. So you're a community over here, and I'm the new guy, and I say, okay, Noir is the second most popular friend over here, so I go and connect with him. The next guy comes. At some point, Noir is not really the most. Is the most connected, so we go to the next one. Or there are ones that you random. So there's different formation. Like if you start in a community, how you form a graph for a physical process, and there is a random graph, which every time I join a community, I randomly connect, throw 3 connectors. So this one says that if things were random, if there was no community in this graph, so this subgraph was not a community, how many edges would I get between the nodes? Now that I think it's a community, how much do I get? The difference of that tells me how far away I am from randomness. And this is what they measure. So let me give you a couple of examples that you use that in machine learning. And this is in recommendation systems. In recommendation systems, let's say Netflix, where we have, 1 to 5 stars. Let's say you have you make, for those of you who attended the collaborative filtering class that I had over here, let's say that you realize that on the average, with your model, you have 1.2 stars error, which meaning that whatever the system gives, on the average, you are 1.2 stars away from the truth. Now, you never really present the results like that. The way that you present the result is that, okay, this is my model, and in order to evaluate and say that it's wrong, what would be the random one? So you take your data and you assign stars randomly. Okay? So let's say now that if you were doing, so for example, this one, will be 1.2 stars, and that could correspond like to a 10% error, or a 35% error. The truth is that the random model will give you around, from my experience, typically give you something like a 2.5 or 3, around 2-star whatever accuracy, like whatever out of 5 stars. And this has to do because your data is skewed, like it will never be from 0 to 0. So basically this is a normalization, because sometimes even the random the random assignment or the random model can be pretty good. If there's no structure in your data, for example, if people were actually, so let's say that was the case, that the way that people buy or watch movies is completely random. So the random model will give you a score, and your model will give you something very close to the random one. So that's kind of like one way of evaluating recommendation systems. And if you read the papers, that's typically how they evaluate them. And another thing is that with K-means, when people are trying to evaluate their clustering, they're trying to find the number of clusters. They say, okay, imagine we're in 2 dimensions, and I had a data set like that. So obviously here there's 2 clusters. And then, but you don't know that. So you try, for k equals 2, you try for k equals 3, you try for k equals 4. Now, what happens is that as you increase k, the number of clusters, your error actually starts becoming very high. So basically, the way to evaluate what is the number, the best k, is that you take the boundary where your points live. You have a problem with this? Oh, okay. So what you do with k-means is that, for a particular k, let's say you had 1,000 points here, you make another experiment where you take these 1,000 points, you distribute them randomly, you run k-means with equals 2, and you see how this score evaluates with the random k. And there's a paper by TBC Rani where he kind of shows, and he has all the mathematics. So for those of you who don't know, TBC Rani is one of the gurus of modern statistics, and he has this book, The Elements of Statistical Learning by Hasty and TBC Rani from Stanford also. So in order to find out if your model, if you're doing the right thing, you always compare with the random k. So you will see, for example, that as you start increasing k, the score you're getting is not that different from, the random k. Okay? So that's kind of like as a digress. Now, what is interesting about this paper, and we'll probably have to keep things a little bit, is that you see the image, figure 1. So basically what Leskovitz and what's the name of the other guy did over here is that they said, okay, they took 230 different graphs that the communities were, they knew the ground truth, okay? And if you read the paper, they got the graph from Ning. They have posted, one of them is like the Life Journal. The one that if we have done, we're going to see today. And they said, okay, for every, so they build a matrix over here. Here they had, let's say, scoring function. Scoring. And here they had communities. Okay. So the scoring functions were 13 and the communities were, millions. Let's call this matrix A. Now, one way to see this matrix A is as a bipartite graph. Here you have like the communities, the scoring function, and here you have, it's kind of like a complete one because everything is compared, connected to everything. So they did a clustering of that graph, or in another way, the clustering would be that they took the correlation matrix, if that makes you more familiar. So this is a 13 by 13. It's a small matrix, 13 by 13, and they they clustered these, so they find correlation. The first interesting thing is that they didn't find any negative correlation, meaning that, if this is high, then the other one is low. But what was interesting is that, and as you can see, they have it very nicely on figure 1, they realized that, so if you do clustering, don't forget, this is a 13 by 13 matrix. A 13 by 13 matrix is also a 13 node graph, and a complete one. So they did clustering on that graph. Or another way, if it makes you feel more comfortable with correlations, they found that they clustered things according to their correlation. So things that they correlate together, they belong to the same class. Okay? And they realized that actually it makes sense. So the scores on the A category were correlated with the one classes. So basically they verified that this categorization that we've done for this scoring function is actually true. Okay? So there's no correlation because internal density and expansion. But there's a correlation between internal densities and edges inside and others degree and blah, blah, blah. And then we won't have time to talk about that. They analyzed the performance. Okay, this is section number 3. And they have like 4 different metrics, such as, do we have anybody left or joining? Separability. So they have separability, density, cohesiveness, clustering coefficients. And they kind of like show how how these scores behave. And it turns out that there's no clear winner. Things are more or less close to each other. Now, I'm going to describe very quickly their algorithm, which I've started coding, and we probably won't have that much time to. We'll kind of like try to code it together, code it up to a point. So, do we have any questions so far?
So this algorithm we're producing or helping produce, we're basically taking a graph and then from there output a score or number of scores.
So basically,
or what?
So this graph is a graph that does 2 things. One is like when I give you a seed node, so I'm giving you Samir, and I ask find me the community that you belong to, all the communities. So the labels, or find me all the people in his community. So it's kind of like instead of evaluating the communities all at once, you compute the community one by one. I mean, it is possible that a person can belong to more than one community. So anyway, the algorithm does something very simple. It computes the page rank through a random walk. And you might have noticed that for those of you that come pretty often in this meetup, there's 2 algorithms that I recycle all the time. One is, and they're actually connected. One is PageRank, and the other is a singular value decomposition. These are like very, very basic algorithms, and if you know these 2, then you can do a lot of things in machine learning. That's kind of like the goal of this meetup over here. We can dive deeply into more complicated algorithms, but I'm trying to keep it as simple as possible. So, and the page rank, the important thing is like the random walk. There's several ways of evaluating page rank. Okay, so the idea is that you start from a seed graph, a seed node over here, and you are jumping from neighbor to neighbor, and you are computing the page rank. Okay. Now the idea is that as you're starting from this seed node, at some point, you will hit a node where the page rank drops below a threshold, and that's where you stop. So basically, and I'm going to show you how we compute that in Python. You compute the page rank, and then from that, you order. So eventually, you will end up with several nodes and their corresponding page rank. then you sort these nodes according to step number 3, and you compute the scoring function according to the, you pick one of these 13 scores over there, and then so basically give you an idea. If you see figure number 4, let me try to reproduce it. So basically, this is your score. And this is K. So you start computing, so you find the local minima. So all these points belong to one cluster, these points belong to a different cluster, blah, blah, blah. So the points between the stars, the local minima, are the community. Now, I forgot to mention something important that just came into my mind. One of the important things about these scoring functions is that we know that they are good because they are monotonic. In the sense, if you keep adding, and that's kind of like where this technique is based, if you keep adding points in the same community, so you add a point that belongs to this community, and you recompute the conductance, so you recompute the, edge density. This will keep increasing. Now, if you add a point that doesn't belong to the community, then this should get worse. Okay? Do you understand that? Is that obvious?
Can you repeat that again?
So, you start from these 3 points and you compute, let's say, that it's between density, whatever. Now, you add this point, whatever score you're evaluating, it keeps improving. Sorry. So you start from these 3 points. You add this point, the score improves, the score improves, the score improves, the score improves, the score improves. When you jump over there, the score becomes worse than it was before. Okay?
That's the local minimum.
And that's where you say, dependence, minima, or optimal, whatever you're evaluating. So, and this is the reason why this algorithm over here works. It says local optima here. Yeah, it can be local minimum or local maximum, actually, depending on what you. And they do have, the evaluation, and then. So basically, what we've learned so far, and we have 10 more minutes over here. We'll switch Python. Basically, I think, and for those of you that want to, work further, I think it's a very interesting paper. It's kind of like, you don't find papers like that quite often because it's a review paper, meaning that it takes, a lot of methods and it compares them. And also it gives you a very simple practical algorithm, linear scale that you can compute, you can code that very easily in Python. So I'm going to focus on the first part, which is computing page rank nibble on Python, because the rest is really, really trivial. It's just a thresholding, And also, if you want more details about this algorithm, you can always go back to this paper, the local graph partitioning and the communities from SIDSET. These are the reference number 2 and 24. No, number 2 and 3. Yes. Okay, let me try now to connect to. Do we have any questions so far?
Have you begun coding the Python thing, or how are you going to
Yeah.
go about coding that?
I will show you the. Let me see how I can share my desktop. Okay, so this is the web page for the big data, large scale machine learning at NYU. How does this look on your screen? You don't, okay. Okay, so you can read it. Let's see, can everybody read that? Let's see from the remote students. I'll stop sharing for a moment to see if there was any. Was everybody okay? Could you see my code, my Python code? Let me share again. If you cannot see, just open your microphone and tell me, because when I'm sharing, when I'm sharing my desktop, I cannot see the chat. Okay. I can increase the font. Okay, so I don't know how to do this now. So I have on my laptop, I have installed I have downloaded the live journal graph, and if you see the format of the live journal graph is that it has 4 lines of comments. It's about 4 million nodes and 40 million edges. So we have about 4 edges per node.
Where can you get that?
If you go to the class website, on the meetup announcement, they have the link. It's from Stanford.
Oh, okay.
Stanford has. You can find more graphs over there. And then it's like source and destination edge. Okay. Now, some of you might find this trivial, but it doesn't hurt to do. So here, I don't know, I think that there's a lot of people that they don't really know much Python, so I try to keep it simple without the functional forms and all that stuff. So this one, opens the file. We just keep the first 4 lines, and we define a dictionary called graph, and we start reading. I didn't check it, but I believe they are separated by a tab. It's kind of like important in Python. Python, when you read a line, always leave the end of line in the answer. You have to split that out. Then, you have to convert this to an integer because it reads as a string. Now, so graph is a dictionary of lists. So basically, if we've never really seen this node before, node has an integer ID, then we just create a new entry in the dictionary where we have a list. The same thing for the source and the destination. Now the critical part is because this is an undirected graph, whenever you see an edge, you should always remember to add it both ways. So there's kind of like redundancy because this graph will end up storing 80 million edges instead of 40 million edges. But it's important to do that you will see next why. It's not completeness, but finding out, how many, who else is pointing to me, it will be too difficult computationally, so we need to do that. Now, so the PageRank Nimble, what it does is that it starts if you go to this paper by Ray Anderson, the local graph partitioning using PageRank vectors, and you go to 2.3. Sorry, I'm sorry. I think it's the other paper. Okay, that's actually the other paper from Ray Anderson and Kevin Lang, the communities from seed sets. When you go to 2.2, does everybody have that? Again, you can download it from the class resources. It's called Class 8. If you go to the meetup announcement, there's a link to the class notes, the reference notes, and from there you can find the paper. So it says that you take the degree of the seed node, and this is the degree of the seed node. So basically, we find in our dictionary the list of edges of the seed node, and we take the length. Okay, so you understand that this is degree. Okay, and then we have to compute the volume. The volume is that for every neighbor of this seed node, we aggregate the degrees. Okay, so for this particular node, we go to his first neighbor, find out how many degrees he has. We keep updating this sum. And the current page rank we have is only for this seed node, and it's the seed node degree versus the volume. Okay, so if you see about that's kind of like the opposite of the expansion. Is like I point to 10 nodes, and this 10 nodes point to that volume. Okay, now we start running an iteration over here, and that's probably not complete because it needs to be broken sometime. So now we're trying to compute the new page rank. So what we do is that in the page rank that we already have at this particular stage, so let's say, for example, in the first stage, this page rank has only found the page rank for the seed node, okay? We go through all its neighbors, sorry, and now these neighbors are going to inherit the page rank, okay? We understand that? We start from a node. Again, if we have any questions, don't contact me through chat because I cannot see it right now. Just talk. Open your microphone. So basically, for every what happened? What I'm doing is that, I start from one node. This node is going to give page rank to all its neighbors. So if I haven't really seen this neighbor before, I create an entry in the new page rank, okay? And obviously, this node is going to inherit page rank not only from the node that I'm examining right now, but it will get page rank from other nodes. That's why you see here an update. It's like a plus equal. So for this neighbor, I'm getting the page rank of the node that is sitting on it right now, that I'm examining, over, divided by degree of the node. Because what happens is that, as this keeps increasing, like this page rank might have at the next step, 10 nodes, okay? Now, at the next stage, there might be 3 out of these nodes that they give page rank to a new node. So every time I'm examining those, I'm updating the page rank of this particular neighbor. So when I finish all of them, I just go and examine and I see all the page ranks if they are above epsilon. And if they're above epsilon, I keep them. If not, I don't consider them anymore. So this threshold eventually, will stop you from expanding to the whole graph. Because what's going to happen is that at some point you will give page rank to some nodes that they don't meet that threshold, you're not going to consider them. Next iteration, again, the same. So you will stay constrained within a community. Now, we got a few more minutes. This is, in my opinion, a more efficient implementation. It's not very intuitive. What I try to explain with the page rank is a trick over here, and let me explain why. For those of you that have, again, attended the class before, page rank can be expressed very neatly with linear algebra, where you have a matrix over here, which is your graph, with a node. And this graph you have already, so for example, it's like normalized. Here, every entry had been divided by the number of nodes. So this is over 3. This can be like over 10. I'm not loading everything. And, you start with a vector. So basically, your seed node will be somewhere here. You do a multiplication, and you come up with a new vector. I think, we've talked about that several times. So basically, that's what it does. This will go to all, this particular node that has already a page rank. We'll find all the ones that it points to, and it will make them non-zero in this vector. And then you will take this one back here, and you will recycle, and it will convert somewhere. Now, this is a nice algorithm when you're computing the PageRank globally. So if you were starting like from several, non-zero values over here, this is an efficient implementation. But as you can see, when you're searching over a large graph, and you multiply, for example, this with this one over here, or this one, like there's a lot of rows that the dot product is going to be zero. So don't forget, you're looking at a very small community of 1,000 nodes into a graph with 1,000,000 nodes. So multiplying this vector every time with all the rows is just a waste of time. This is why, I do a lookup first, I find the neighbors. So basically, this step that I described before kind of identifies the subset of the graph that is of any interest. And the subset of the graph that has interest is only the graph that has non-zero values along this column over here. Okay? Do you get the idea? Is it clear? Mm-hmm. Is it clear for the class? So I just wanted to make, because I always like to give a computational flavor of machine learning in my classes, and that's kind of like my expertise. Yes, the traditional, and this is how it's presented on the paper in terms of linear algebra. It shows you something like that over here. No? It's equation number. It doesn't have an equation number, but it's the third equation on 2.2. This one, I don't know how it is. Yeah, M equals 1/2 of identity matrix plus A P minus 1, blah, blah, blah. So, yes, so that's the story. If you wanted to, if you really, really wanted to, use this approach, the linear algebra one, you can do it, but it would not be very much computationally efficient. So the idea is that basically you are using, equivalently, you are using the non-zero value of this matrix, and you identify the portion of that matrix that you have to work on. Okay? So once you compute that, once you compute the nimble PageRank, the rest, as it's described on the paper, is, is fairly easy and straightforward. Then you have to take these values, normalize them like that, and take the... Now, I want to point out that in step number 3, it's kind of like a cumulative function. In step number 3, it says you compute the F, whatever score, for Sk, where I is less than K, where K is your... and you do that for every K. Okay? And there's like, you can compute that recursively because, but maybe it doesn't matter. I mean, you can do it no matter how you do it, it's going to be easy. I mean, once you compute it for K equals 5, computing that for K equals 6, you don't really have to do everything from scratch. Like the nice thing is that this evaluation function, if you have compute like for F5, the F6 is a simple update of the F5. You don't have to take, and recompute everything, just like as a node. Do you have any questions from, from the crowd?
Pretty awesome. Is there any algorithms that you can use?
Yeah, I will post the source code. Yes, it's, I'll finish it and put it on. But pretty, yeah. So,
is there any algorithms that you can use that also typically
so weight it. Yes, you can do that. I mean, in fact, like spectral algorithms, for example, which are very similar. You can modify this algorithm and use the weight. So yeah, the question was that if we can use the weight. Another way to see that would be if you had like multiple edges between two nodes, kind of like give you the strength. But yes, you can. I think. You can definitely compute PageRank by, replacing. So basically, the difference will be, instead of dividing with the degree of the node, we will divide with the total weight. So if every node, every edge has a weight, you will take the sum of this weight, And of course, be careful, don't put negative, just like we never really say that, but all these algorithms in graph algorithms, they work only for positive ways, okay? Graph theory becomes really, really weird when you start putting negative, especially if you have cycles, then you have things that they don't make sense. So yeah, just be careful, like as a debugging stage, if things are going bad in your implementation, always test that. So the most common bug is at some point you use negative weight. Another thing can be you forgot to normalize, okay? And you might have outliers. So basically, whenever you work with things like that, try to remove nodes that they connect with everybody. You have a node connecting with everybody, and this is a problem. Okay, anything else? I think we're about to sign off over here. It's going to take you a little time for the next meetup. I know I've been very busy lately. There's also a meetup today which probably you cannot attend if you haven't registered, a data science one at Google. I'm going to be there. Yeah, is this algorithm dependent on choice of the seed node? Obviously, because you are your seed node, it's kind of like a query. Like for the database people, this algorithm is like a query algorithm. Find the community or find all the people all the nodes that belong to the same community to this seed. So for this particular seed, it will give you the community around this seed. So, for example, if you wanted to detect all communities, you have to run that for multiple seeds. So you run it for this seed, you take out all the communities, and you move to the next one, blah, blah, blah. So, also have to, what worries me about this meetup is that people are not very consistent on their reservations. And I think we're around 10 or 12 like steady ones. But if we fall under that, then probably it doesn't make sense to meet in person instead of meeting. So anyway, but maybe it's the time. All right. Probably the next one will be working on these things with GraphLab. People have expressed interest in GraphLab. Okay. And we'll see how we can expand it. But the nice thing about this algorithm is that you can pretty easily implement that on your own. You don't even have to even with a single computer, you can achieve very high performance by just reading things from the disk. Not like that. All right. Bye-bye, and see you next time. Bye-bye, Samir. Yes, you can. Just a minute. I don't know how to always do problems. How will you end this?